AP Calculus, section 6.4, page 3. All right, here's an example of this exponential growth. Bacteria grown in a certain culture increase at a rate proportional to the number present. There are 1,000 bacteria present now, and the number will double in 30 minutes. If Y bacteria will be present T, I don't want to change this hours right here to minutes so that we have consistent units throughout. Y bacteria will be present T minutes from now. Express Y as a function of T. Estimate on your calculator, confirm your estimates analytically. All right, this first sentence right here, bacteria grown in a certain culture increase at a rate proportional to the number present. All right, Y is the bacteria, T minutes. So, rate proportional to the number present, that's where we start off. dy dt is ky, where k is a constant. And we kind of start working through the process that we've done over the past couple of days in terms of getting this back into a y equals. So let's separate out the variables. I'm going to multiply by a dt and at the same time divide out by this y. So we have dy over y is k dt. Then let's do an antiderivative, so we have to integrate both sides. And the antiderivative of a dy over y, well, that's natural log absolute value y. On the right-hand side, don't forget that k is a constant. The variable is t. Antiderivative of this is kt plus some constant c. Now, we already know that y is positive, so the absolute value bars are not necessary, and we can rewrite this as the natural log of y as kt plus c. I would suggest you put a note to yourself in your notes that says, because y is positive, absolute value is not necessary. Okay, now we need to get this into a y equals. Couple ways that you may have been taught to do this. Some of you may have been taught to, when you have this natural log, to raise e to both sides. And then the e and the ln, because they're inverses of each other, they take each other out. And we have y equals e to the kt plus a c. Personally, I like to think of this as log base e of y is kt plus c. And then I rewrite that into exponential form by taking this base e to that exponent equals the argument y. I don't care which one you use, just somehow you need to be able to get from this line to that line right here. Okay? Now, we need to think about this. Let's see. Y equals, oh, we can separate this. This is same thing as e to the kt times e to the c. Because when we multiply things with the same base, we can add the exponents. I just undid that. And then this e, that's 2.718 raised to some constant. That's just a different constant. So we have e to the kt times a different constant. And let's just rewrite it this way. Ce to the kt. All right, now we need to figure out those constants. Some data that we know. We know way back at the beginning at time 0 there are 1,000 bacteria, and if we plug that in, this e to the 0, that's 1. So we have 1,000 equals C. And another piece of information we have is that at time 30 minutes, there will be 2,000 bacteria. So I'm going to actually have to come all the way up here. At time 30, y is 2,000. And when we plug this information in, we're going to have 2,000 equals C, 1,000, e to the k times 30. I'm going to divide out the 1,000 and we'll have 2 is e to the 30 k. There are two ways to solve this, and I'm going to show you both ways. There's benefits and hindrances to both methods, so let me show you. Probably the one that you're least familiar with, let me show you that one first actually. What if we raised both sides to the 1/30th power? Left-hand side is 2 to the 1/30th. Right-hand side, that's just e to the k. So now we can actually stop right here and we can go back to this equation down here, y equals c e to the kt, and we're going to get y equals c, which was our 1,000, and then e to the k, that's 2 to the 1/30th, to the t, which simplifies all down to be 1,000 times 2 to the t over 30. Okay, looking at the other way to solve this. I believe most of you last year were taught to take the natural log of both sides. So ln2 is ln of e to the 30k, which then became 30k is ln2. If you didn't do that, maybe you rewrote this from exponential form into logarithmic form by the exponent 30k equals log base e, which is natural log of 2. Either way, makes no difference. We get to here. This gives us that k is, ln2 over 30. I switched sides there. ln2 over 30. All right, now when we write back into this format over here, we have y equals c, still 1,000, but this time we're just going to replace out that k. So we have times e to the k, which was ln2 over 30, all of that to the t. So this simplifies down to be 1,000 e to the t ln2 over 30. Whew, that's the answer to part A. Oh my goodness, that's part A. All of this to end up right here for part A. Makes no difference to me which way you solve this one to get an equation. They look very different, but they are equivalent. I think this way's a little bit harder to solve for the e to the k, but your equation looks nicer at the end. This one, easier to solve straight away for the k because you're used to doing that, but then your equation looks uglier at the end. Either way, doesn't make a difference. Okay, so part A done. Part B. Estimate on your graphics calculator how many bacteria will be present in 2 hours. So, go to your calculator, put in one of these equations. I chose this first one because it's easier to type in. My window is set up. X is -10 to 200. Y is -5,000 to 60,000. If I'm going too fast, pause the video so you can get this typed in. Graph right here. And on your calculator, how many will be present in 2 hours? We just have to solve that. That's going to be when X is 2 hours, 120 minutes, because our time is in minutes. So we do a value at 120 minutes, and that means that we have 16,000 bacteria. Done. Part B. Part C. This time in Part C, they tell us that Y is 50,000, and we have to find that time. The way you have to do this on your calculator is to put in the 50,000 as a Y value, graph, then do an intersect. And we will get that T, or in this case, X off the calculator is 169.315. That's minutes. Okay, now part D. Confirm your answers to B and C analytically. All right, the B part's easy. That's just plugging in. So we're going to get Y is 1,000 times, I'm going to use this one, 2 to the T over 30. 2 to the 120 over 30. That's 1,000 times 2 to the 4th, and that's 16,000. Bacteria. For the second part of D, where we're confirming the 50,000 bacteria is at 169.315 minutes, we'll set 50,000 equal to, now again, I think this first one's much easier to solve, so I'm using this one. 1,000 times 2 to the T over 30. Divide out the 1,000. 50 is 2 to the T over 30. All right, I rewrite this back into logarithmic form. So the exponent, T over 30, is log base 2 of 50 multiplied by 30. T is 30. Log base 2 of 50. And your calculator does these different bases now on logs. Let's see, we have 30, and then log you can get under alpha, F2, right here, fifth one down, log base 2 of 50, and this better come out to be 169.315 minutes. Yes! Whew, there we go. Lots to do on this page. Lots to do. We're going to do another one very similar to this, so you're a little iffy on the pre-calculus algebra in there. We'll pick it up again on page 4.